I'm going to start and just give an introduction to Kafka. I'm going to introduce it by way of explaining what it's for, why we made it, what it does. And I'll talk a little bit about the experience at LinkedIn and move on from there. So as mentioned, I was previously at LinkedIn. A lot of what I'm going to talk about came out of that. I came in originally effectively to work on relevance and recommendation systems. But over time, I found myself much more in the infrastructure space, as that was where the challenge really was at that time, was just scaling data systems. So our story kind of begins roughly in 2009, and we were working on Hadoop adoption. And we'd gotten far enough along to build some things that were basically valuable on top of Hadoop. And I think we decided at that point we really wanted to get all the data into Hadoop and get kind of a complete representation of the business there. And be able to pair that with processing. And this was where we were running into some conflict with the unfortunate truth of what all our data was, which was basically like CSV dumps out of databases and these XML log files. And we just had to deal with it. And we put a lot of kind of painful work into just processing this and trying to make at least what we could available in Hadoop to make it useful. Our approach was just like get it done. And after spending a certain amount of time on this, we actually did create a fair amount of value. We were doing recommendation systems that recommended people you may know. We were doing stuff for ads and jobs. But ultimately, we were not covering most of the data that the company actually had. So I think our estimate at that time was we were covering about 14% of what was actually happening in the company was in Hadoop. And also just the amount of manual labor in getting this data available was very high. And every time we added a new data source, like if we wanted to expand that 14%, there was more people who had to do more work. And every time the rest of the business changed, that would break something. So one of the things we started to realize was, hey, these cool data systems or data processing pipelines or whatever are downstream of actually a whole bunch of data. One of these processes will likely put together dozens of data sources, potentially more. And so if all of these data sources are evolving, as you would hope they would be, if you hire a bunch of engineers and get them to work on the upstream code, then it's very likely that all of these processes are going to be breaking all the time. And worse, our architecture was evolving, and we were adding new systems. And so just keeping up with all of that was a huge pain. And so we were kind of solving this in a very manual way, where for each kind of table, we would massage it into some usable form and kind of make it available in Hive. And ultimately, this was not really scalable, especially as we started looking at really trying to get to a complete coverage of the data we had, covering all the different data systems, different data sources. And so, my conclusion, the conclusion of other people on this team was, I guess we got two approaches here. Either we're going to hire an army of people who are just going to munch data, but we're probably never really going to keep up with the rest of the organization, or we're going to try and do this in a more scalable way, right? So we came up with this idea of scalability, not really in a system sense, but more in like a human sense, right? And we wanted to try and build these kind of data load processes in a way that would be kind of organizationally scalable, that you would plan on, say that you're planning on having 1,000 data sources. How would you attack that problem? And let's say that you wanted to represent them well, and you wanted to not have people do work on each one of them. Let's say you wanted new data to be almost like a constant time problem in human terms. And this is what we wanted to achieve. And we kind of started this survey of like, OK, how do things work in the world? How is data flowing in our organization? How is it flowing between different systems? I got interested in a bunch of things that I'd previously not been interested in, like schemas and metadata, where previously I'd focused more on like systems and algorithms. And this is what we found. There was basically millions of little data pipelines in the company between different types of systems. So we had one approach to shipping relational database changes to caches and things like that. So we had a kind of subscription layer for that. We had one approach to shipping database changes to our data warehouse and other kind of relational databases. And we had one approach of shipping it to Hadoop, which was these horrible CSV dumps. And that was just relational databases. We were also getting non-relational databases, and we wanted to be able to get data out of them into Hadoop. We wanted to be able to produce data in our Hadoop cluster and publish it back for serving. But that was just the non-relational databases. The other big area of interest was user events. In fact, I think this is kind of the whatever you call the underneath of the iceberg of data, right? Is event data, like the things that are happening, like what you store in tables is kind of the current persistent state. But what you do analysis on very often, if you're interested in relevance, is what actually occurred. What did people look at? What did they click on? At least for a web company. But actually, any type of business has this type of event data that tracks what's happening. We had this kind of terrible pipeline where we were, aggregating logs and kind of r-syncing them around over NFS things, and eventually they would make their way into Hadoop, and that was pretty fragile in its own way. And that was kind of like business events, but we also had application logs that were, errors, that kind of thing. We had messaging systems. We had a pipeline for metrics or operational data, stats on individual servers. And so each of these were not that bad in their own way. Like when we worked on each pipeline, it actually kind of made sense that we had built out that pipeline in the way we had. And each of them were limited in a way that was like maybe OK for that use case, right? So some of these pipelines were relatively high throughput but lossy. Like we didn't really have any strong guarantees on the delivery of event data. Some of them were relatively reliable, like the database log shipping, but they were not particularly scalable. But when you put them all together, it was actually kind of a mess. And the reality was managing all that complexity as we scaled was actually quite difficult. And it meant that getting a particular data set was actually very particular to the part of the business and the system it was stored in. And so getting data was always kind of a research project. And we felt that, like, hey, this is kind of the most important thing. If you want to do analysis, the first step is always make the data available, make it well-formed. Like high-quality data is the first step of any kind of real use of that. If you have that, of course, you don't think about it. But if you don't have it, you spend all your time on this kind of low-level munging. And this was developing into almost like a set of beliefs among the data scientists in the organization that, like, 90% of the time would be spent on getting data or low-level munging or parsing out these XMLs, which is really kind of sad if you think about it. Somebody spent the time and got like a PhD in physics and learned all this cool stuff, and then now it's like here work on regular expression fields out of malformed XML. That's not really the goal. So. But worse than just kind of like the cost of that, where there were a lot of things that we couldn't do because data in one system was not available to other systems. So a lot of our operational data was not available in Hadoop, and you couldn't run any kind of deep analysis on how we were running stuff in our data center. You could do real-time monitoring, but not deep analysis. Likewise, a lot of the things that were happening in the business were only available in the data warehouse and Hadoop cluster. They weren't really available in the real-time monitoring system. So you could get this kind of daily reporting, but you couldn't find immediate problems. And this went on. And basically, plumbing every one of these other systems together would be far too much work. We were barely keeping what we had afloat. And being, kind of at least by that time, an infrastructure person, if you're an infrastructure person, naturally the solution to any problem is more infrastructure. And so we came up with this idea that we would try to have some kind of platform for real-time data. We would have some kind of platform for streams of data. And the inspiration was definitely Hadoop, which had been this really effective kind of data warehouse or warehouse platform where we had the kind of big long-term archive of data. And we thought, hey, look, if you kind of step back and squint a little bit, all of these weird ad hoc pipelines that we've built, they're all instances of the same thing. They're all representing some kind of stream of continuous changes. If we could represent that and somehow get the good properties of each pipeline that we had built and get none of the bad properties, then we could have this kind of central repository that would allow that kind of real-time data interchange and processing. This is what we wanted to achieve. We didn't really have any idea how to do it. And so that was when we started thinking, well, like, surely this is a solved problem, right? Like, so we're not the first person to try and send a message from one place to the other. And so we started with traditional kind of enterprise messaging systems. We were running ActiveMQ at that point for certain parts of the site. We also did some evaluation of RabbitMQ. And we basically put them against that set of problems. And the question was, can we get something that would actually solve all these problems? And in fact, we were not that successful. We did tests on production load, and there was a bunch of issues. So throughput for kind of high volume event data was not quite there. It would have been relatively cost ineffective to try and run these through a messaging system. And the integration with a batch system to run like ETL was not very good, right? So the reason for that being when these message queues filled up with data, they would kind of get slower and slower and eventually kind of tip over. But you can imagine a Hadoop cluster, it may go down for maintenance for hours, and you need to buffer everything that happens on the site during that time period. And this was all kind of a property of not really having taken persistence very seriously inside the messaging systems. We wanted to be able to do high-level stream processing on top of these streams of data. In fact, that was one of our primary goals, which I'll talk a little bit more about in a second. And the messaging systems had not really been built with that in mind, and it kind of showed if you tried to think of how you would do that integration. And finally, ordering guarantees in a distributed setting where you have many consumers of data were not very strong. And why would you care about ordering guarantees? Well, you would care if you were shipping database changes or streams of profile updates or customer accounts or whatever. Anything where there's mutations of state, it's really important if you're shipping, say, updates to user profiles into a search index that the first update gets in first and the second update gets in second. Otherwise, if you flop that order around, you're going to have a permanently inconsistent search index. And this is true for a lot of these types of stateful replication problems. And so these are kind of the problems that we saw with traditional messaging systems. And we realized we weren't going to get there that way. Our second approach was to basically build Kafka, which would have kind of similar APIs to a messaging system, but it would be different, actually quite different in terms of how it was implemented, quite different in the role that it would play inside the organization. And I'll walk through a couple of these differences and just try and say what we built. This kind of came out of the fact that basically the main people working on this system had been involved in databases, and so we had a very particular idea of what messaging system might look like, which was basically the back end of a distributed database. And so in terms of its usage, Kafka is not that different from a messaging system. Like basically, it has an open API to publish data. It journals that data and keeps it stored, and it waits for people to consume that data. They do so on their own time frame. So it's not like conceptually totally different from a messaging system, but I'll walk through a little bit of some of the differences in internals. So the big difference is in the primary abstraction that Kafka provides, which is this idea of a kind of commit log. And so internally, what Kafka is giving you is this log or journal of changes. And it's persistent, and it's replicated across machines, and you can have lots of it. So it's like a very cheap abstraction. And so why would you have a commit log in a messaging system? It doesn't totally make sense at first glance. But this is obviously like kind of one of the core abstractions inside of a database or a distributed system, often for replicating changes. And I'll talk a little bit about that in a second. What this is meant to represent is a sequence of records. Each record is given a number, like 0, 1, 2, 3, 4, 5, in increasing order. New records are appended on the end. So this is kind of time going from older to newer. And readers of that data would kind of read from old to new. So this is the key abstraction. If you were to peer inside of modern distributed systems, you would see these kind of commit logs all over the place. They're inside of HBase or whatever. Usually it's not an end in and of itself. But it turns out if you think about what's happening inside of a distributed system, it's not that different from publish subscribe messaging. Updates are coming into one node and it's broadcasting out to replicas, and the performance has to be very high. The correctness has to be very good. You have to guarantee that all of these replicas maintain the same state. And so, so since we were kind of aware of this, we thought that, hey, this is really a good abstraction. We want to be able to do it not as an internal implementation detail of one distributed system, but if you kind of step back and you see your whole company as one big nasty distributed system with different pieces here and there, you could use the same kind of log, commit log, or journal to broadcast data out consistently to everything in the company. And so to use one of these logs as a publish subscribe messaging system, you have some writer who is writing here. You have readers. Each of those are at some point in the log, and they kind of control their pace and position as they read along. And so one of the nice things about this is you can reason about the point in time of any of these destinations or systems or readers. You can say, OK, this reader is at point in time 11. Now, 11 is just a logical timestamp. It's not really physically the time. And as a result, you can actually, if you have multiple things feeding off of this, you can actually reason about where each of those things is at. What state are they in? Because you can say, OK, look, they have consumed everything prior to 11 and nothing after it. And it turns out a topic in Kafka is basically a sharded set of logs. That's basically the fundamental thing. So when you publish data to a topic is basically a category if you're not familiar with messaging system terminology. When you publish to a topic, you're basically just writing into this partition set of logs. These are spread over a set of machines and replicated for fault tolerance. And so any of those machines can kind of die, and we won't lose your data. But fundamentally, that's what we're providing is this commit log abstraction. I'm going to walk through a couple of implementation details just to give people a flavor for what's going on under the covers. If you nod off during this section, that's OK. I won't be offended. So I'll talk briefly about replication. I just showed that sharded commit log. Those shards are basically spread out over a cluster. Each machine in the cluster is acting as a leader for some of those logs or shards or partitions. And some are acting as a follower. So here I have a topic named A, and I have a topic named B. And A has partitions or shards 0 and 1, and B has just shard 0. And it looks like A has a replication factor of 3, and B has a replication factor of 2. OK, so you can kind of follow the write path in this diagram. If a write came in for A0, it would come into server 1, and it would replicate out in parallel to the two followers, server 2 and server 3. If something comes in for B0, it's going to replicate out to the single follower. And there is in the cluster at any given time, there's a single kind of controller process. And it makes all the decisions about who gets to be leader or follower. And it controls the placement of shards within the cluster. And so it's the kind of single brain that makes those decisions. It's not a scalability bottleneck because there's not that many shards and decisions to make. There's just thousands. Question in the back.
You said that the logs are sharded. Is the data in them disjoint, or is it?
Yeah, that's right. So, OK, so the topic is made up of a bunch of log shards, and then each shard is replicated. And so in this diagram, A0 is one shard, and A1 is the other shard. Each of those shards is then replicated, some replication factor of your choosing. So you would say, look, I mean, usually there's not that many reasonable replication factors, like 1, 2, or 3 are usually it. I mean, maybe 5, I don't know.
But the messages in A0 are not the messages in A1.
The messages in A0 are totally disjoint from the messages in A1 unless you happen to put the same message in both. So yeah, that sharding or partitioning, that is how you scale out your data size. And replication is how we ensure fault tolerance if one of these machines dies.
So if a reader wanted to reconstruct the original ordering,
yep,
I would have to read some from A0, some from A1, and some order.
Yeah. So the model we give you is we give you a total order per log. And so you can partition something up by a key, but there's not a total order over all messages unless you only have one partition. So what does that mean? Most systems that claim to give you a total order over all messages, they do that by having one partition, right? If you want to spread that over a large cluster of machines and you don't want them to have to coordinate, then you're going to have different orderings. How would you handle something like updates to a database? Well, it depends. If you have a database which internally has some partitioning scheme, maybe like MongoDB, then their partitions would probably map to our partitions. If you have a database which is centralized like MySQL, then you effectively just have one partition. If you want, you can broadcast that out to multiple partitions and partition by the primary key of the table or something to ensure that your updates are ordered. Does that make sense? OK. Yeah, question?
So are A0, A1, and B0 topics?
Yeah, so in this diagram, A and B were topics. 0 and 1 were partitions within that topic, if that makes sense. So coming back, this was meant to be one topic with 3 partitions. So hopefully that makes sense.
And how is the decision made which chart to send the log to?
Yeah, so when you create a topic, you say, hey, I want to make a topic. I want to have 100 partitions. We basically place those within your cluster. And so we say, OK, we need 100 partitions. We're going to put them here, here, and here. We kind of try and spread that balance. And then we spread the replicas so that the replicas are never on the same machine that the primary is on. Otherwise, you don't really get fault tolerance. And so that controller is making that decision.
But there's no guaranteed algorithm for distribution.
Oh, can you repeat the questions for the video?
Oh, yeah, sure. Yeah, so the placement algorithm is actually relatively simple. It's kind of like a round robin. However, if you care to, you can actually place partitions where you want. And then you can move them later. So partitions are actually totally movable in the system. If you basically execute a command and you say, oh, I want to move this partition from this machine to that machine, you can totally do that. It'll basically execute in the background. The way it does that is, let's say there's 2 replicas for a partition, and you say, I want to move it. I want to move one of those replicas to this other machine. What it does is, under the covers, brings up a 3rd replica, allows that replica to catch up, and then kills off one of the old ones. Question?
Do your partitions have to be the same size? Like if you have EC2 nodes, they'll all have to be identical size?
Yeah. So the servers don't have to be the same size. However, we don't do a ton. So you can have servers which are all different capacity levels. We don't do a ton right now in terms of partition placement to help you balance so that your bigger servers get more than your smaller servers. So you would have to do some kind of scripting to do that placement correctly according to whatever your machine capacities were if you wanted that. Other questions?
How do you handle splitting and joining?
Yeah, we don't. So the question is, how do you handle splitting and joining topics? The answer is you can add partitions, but we don't do anything in particular to the data in the existing partition. So if you have one partition, you add a second. Maybe you have a bunch of data in the first partition. We'll add a second partition. There's nothing in it. As you publish messages, presumably you would publish it to the new partition. If you want to, you can read the old stuff and repartition it into more partitions. In ARM, this is, however, a over-partitioning model. So the assumption is partition doesn't mean machine. It just means data chunk. And so you might have 2 machines. You might have 100 partitions spread over them. You could keep adding machines and moving load until you had 100. And then you can't get any bigger than 100 with 100 partitions unless you add some partitions. Does that make sense? Cool.
What happens if a machine with the controller goes down?
Yeah. So the controller is also highly available. So if the machine with the controller, I said, oh, there's this magical controller that's making, is this some kind of single point of failure? The answer is no. The controller is also highly available. So if this dies, then we will first re-elect a new controller and then re-elect leaders for the partitions who are on the machine. So that failover will take a few milliseconds longer, but it's not like your cluster is down or anything.
Is there a way to understand what the correct number of partitions would be?
Yeah, that's a good question. So the question is, what's the right number of partitions to pick? I'll give the short answer, and I'll give a pointer to the long answer. The pointer to the long answer is we just wrote a blog post on this. It gives every nuance of that question. So if you go to blog.confluent.io, it's one of the first few ones. But the short answer to that question is the number of partitions determines, in some sense, the parallelism of that topic. And so it'll have 2 impacts. The first impact is you can't really add more servers than you have partitions. So if you have 10 partitions, you could spread those over 10 servers, but you can't spread them over 11 servers. I mean, you could spread replicas over 11, but basically, you see what I'm saying? So your throughput will never go beyond the write capacity of 10 servers if you have 10 partitions. The second issue is partitions are consumed by a single consumer process. So it's the unit of consumer parallelism as well. So because we want to give an ordered stream of changes, you can't obviously have an ordered stream consumed by 2 threads on the same machine or different machines, because they would have to coordinate about each message. They would effectively stop being 2 threads, or they would process messages out of order. Right? So if you want to have an ordering model, it has to be in line with your partitioning model, and ours is. Which leads into this next slide, which is how do we scale consumers? So that's great. We can scale data in the cluster. but what are you going to do with it, right? So the way that that works, these are these partitions again. I've used a confusingly different notation. I don't know how that happened. And typically messaging systems, the consumer is a process, but for us, we're going to consider a consumer to be a pool of processes. Could be one process, could be more. And so I'm going to call that pool a consumer group. And so one logical group is going to consume everything in my topic, right? And what I mean by that is every message in my topic is going to go to some consumer in that pool, okay? So if I have 100 messages, then probably about 50 of them will go here and about 50 of them will go there. And that division actually happens by partition. So I'm going to take some of my partitions and assign them to this guy. I'm going to take some of my partitions and assign them to that guy. Okay? I may have another consumer group which is consuming exactly the same data, the exact same set of messages it's consuming, but it's actually spreading, as you can see, a little bit more finely. So there's 4 total partitions. This has 4 consumers. Each gets 1 partition. This has 2, so each gets 2 partitions. You can imagine another consumer group with just 1 process, and that single process would get all 4 partitions all to itself. So I can't have more than 4 things which consume 4 partitions, but I can have as few as 1 if I want. Does that make sense? For some reason, this is the most confusing thing in the system. I don't know why. It's just hard to understand. So if you're used to traditional messaging systems, I think this probably, I mean, each messaging system is a little different, but like JMS type systems, I think this kind of generalizes the idea of topics and queues. So within a group, it's like a queue. Between groups, it's like a broadcast pub sub. And so by choosing, a group is really just how you label the process when it connects. So by choosing that, you can basically get any mixture of publish, subscribe, and queuing type use cases.
Do you have a picture with partitions and replicas? Do replicas factor into?
Yeah, replicas basically don't factor into the consumer story. Every machine will be both a leader, and a replica. It's a leader for some partitions. It's a follower, a replica for other partitions. All the reads and writes always go to the leader. But load is balanced because everyone's both a leader and a follower.
But a consumer could read from any of those replicas.
Actually not. So there's a number of details to having a fully correct, consistent, replicated log. And one of those details is just because somebody has given you a message, it doesn't mean you can give that message out to other people. So the question is it legit for consumers to consume from replicas? The answer is no. Actually, one of the things we guarantee, which is a little bit more esoteric, is we guarantee that consumers don't see messages until they are fully committed. Fully committed in a log replication algorithm means even if you were to immediately kill any node in the replica set, that data would not be lost. And so it has to be the case that you give that guarantee if you don't want to see weird phantom reads or different readers get out of sync or whatever. And in order to give that guarantee, it's actually not OK for a replica to give out data because it doesn't know what everybody has gotten. So it doesn't know what's committed and what can be guaranteed. It knows, hey, I got this new write, I'm applying it, but it doesn't know that that write can or can't be lost. Only the leader knows that. It's a little bit inside baseball, but yes?
So in the previous slide, so for C1, C2, it's
Yeah.
on them, the onus is on them to coordinate if they want some kind of ordering, right?
So the guarantee that we give is we assign each partition to only one consumer. And so the ordering guarantee we give you is within a partition. So I showed that kind of sharded log. Each log shard is totally ordered, but between shards, there's no ordering. Does that make sense? Right. So if you think about if you were sharding up updates to a database table, you'd have 2 choices, right? You could have a single partition or shard, which would totally order all updates. Or you could shard it by some primary key, and then you would be guaranteeing an order by that primary key. Like maybe all the updates for a particular user are ordered, but you wouldn't guarantee it across everything. That actually maps pretty well to the real world, where you either have multiple processes which are moving and are in an uncoordinated way. They're either multiple partitions in a database or multiple servers which are tracking events or whatever, in which case you actually have no total ordering over everything. Or you don't, and you have some centralized system which is totally ordered, in which case it really maps to one partition.
Right, and since you have more than one partition, then you need some coordination, and the producers and consumers will have to understand.
Yes. So that sharding is done by the producer. So it chooses a key which will choose the distribution of data, and that key would have to be what the consumer wanted it to be sharded. Cool. Question in the back.
So the partition method that you use, you said the non-roaming partition method. Why not use the partition key based on something in the message itself?
Yeah. So the question is, just to restate, how is data partitioned up? And so there's really, I'm going to actually divide that question into two parts. One part is what I was asked before, which is how are partitions physically assigned to machines? Because each machine is holding lots of partitions, maybe 1,000, right? And the second question is, how is a message assigned to a partition? So it's the same two-level mapping you would see in most distributed databases. So data that is published is assigned to one of these partitions, either by the key that is given with the message, if there is a key, or if there's no key, at random, round robin. And then partitions are assigned to machines effectively at topic creation time in kind of a random fashion, or you can actually move them around. You can say, I want that partition and put it over here on this machine. Does that answer your question?
Yeah, so you did mention that you can assign a partition key to...
Yeah, you, the producer of data, control the partitioning of data. If you choose to ignore it, we basically choose something random to partition on.
Because that could be used potentially for balancing your data across partitions.
Yeah, it's used for balancing and also controlling what things are and are not ordered. Because our ordering guarantee is always within a partition. Other questions? Question in the back.
So, in that case, different consumer groups want getting same information from the topic, but they have a different time period.
Yeah.
So that means if I have to publish one message to the P0, so how long should I keep that message?
Aha. OK, this is a good question. So you publish data. When does it go away? OK, so most systems, most messaging systems are very aggressive at trying to get rid of messages as quickly as possible. We actually have a really different model. We're basically maintaining a log. So we actually don't pay any attention to where the consumers are. And I'll give some explanation. It sounds crazy. We maintain some fixed SLA. We say, look, we'll maintain 7 days. 7 days is pretty normal at like LinkedIn. They'll just maintain a week of data. If you can't catch up in a week, then you're out of luck. On a per topic basis, you can adjust that. You can say, OK, I want to maintain this topic forever. I want to maintain this one for a month, this one for 7 days. The reason that that is important is because in any case, if a consumer, the way other messaging systems work is as a consumer falls behind, they maintain more and more data. And then they kind of tend to get slower and slower. And so you might as well just kind of budget for this worst case, maintain your fixed SLA. You have to handle that worst case anyway. And that's what we do. So effectively, you set a retention policy with a topic. That's either going to be by time, meaning keep 7 days. It can be by size, meaning say, hey, keep a terabyte. Or it can actually be by key, which is a little bit more esoteric, but allows you to keep the last update for every key. So you can guarantee that you can do a complete restore off of that topic and get every key, which is really useful for mutable updates, which are kind of a advanced topic. Cool. OK. All right. So our goal here was really turn this into kind of a modern distributed system for events, streams of events. To really hit all those use cases I described, you have to get a couple things right. So you have to have scalability, which is similar to a file system. This was important for our logging use cases. People who do logging events, they know you get lots of them. And if you are replacing something which is basically logging out to disk in a very simple fashion, you can't replace it with something which is much slower, or it's going to take a lot more machines. So to really match a file system, you have to be in the kind of hundreds of megabytes per second per server range. You have to be able to maintain many terabytes per server you add. To handle the kind of flow of important database updates, we felt that you had to really be able to give the kind of guarantees that you would get out of a database. You need to be able to maintain that kind of strict ordering I talked about. Data has to be truly persistent in the sense that it won't be lost even if one of these machines is killed. And then finally, for all of this, we wanted it to be distributed by default, right? So we wanted it to be something which you operated as a cluster. I think different systems attempt this and are successful to different levels. But like from my point of view, HDFS, the Hadoop file system is actually pretty successful at this. You think about writing to the cluster. You think about creating a file on the cluster. You don't so much think about as doing that on particular data nodes or whatever. And I think that's actually really changes the way a system gets used. I think it changes the way a system gets operated. So that kind of as a cluster operation is one of the important things we wanted to do, as well as being able to scale out the producer, consumer, and broker layers all horizontally. And so that's Kafka. And that was really became the thing that we used as this kind of stream data platform. And then as we were working on this, we were spending a ton of time getting each of these different data sources kind of fully instrumented. So we were publishing everything. So we started with these business events that we were tracking. We got all of those available as real-time streams. We moved on to operational data sets like the application statistics and logs and errors, traces between services as they called each other. And the last part of that is basically the database changes. And as we were starting to make these different data sets available, a whole slew of use cases started to open up. So we got a pretty advanced monitoring system that fed off of these streams. This became kind of the primary system that we used to make sure the site was working, but also like the system we used to make sure the business was working in real time. And this all kind of flowed through these Kafka streams of data. And we also started to grow up infrastructure for processing these streams of data as they occurred. So that's an area I'm going to dive into in a little bit more detail. Question?
A question on latency from when a transaction first comes in to coming out of So and what you can fine tune with that kind of push and pull.
Sure. Yeah. So the question is, what's the latency for these Kafka messages? So there's some tunables, and then let me talk about just kind of the inherent latency that's there. So when you do a write, we're basically writing it to that leader. All the followers are applying it in parallel, and then it's available to the consumer. That'll take about 2 milliseconds on a good network if you're not buffering in your producer. We do allow you to kind of tune the producer for higher throughput, and it will buffer up more messages and kind of send them all together, if that makes sense. So, but assuming you're sending messages kind of as they come to you, you would expect a couple milliseconds. This is basically the speed of light. And as of course you get more overloaded, that would slow down.
Okay, so you can have lower latency, but then you get a little bit less overall throughput.
Yeah. So one of the things we've done in at least the Java client that's relatively sophisticated is try to capture this trade-off between latency and throughput. So the most efficient thing for a computer network, for the I/O that writes to disk, for the I/O that replicates to other machines, is basically to do big batch writes. But batching, of course, adds
like
latency.
on an order of a half minute or something, or
no. I mean, basically, to get good throughput, you actually just want to send chunks of data that are more like, 4K, 8K, 16K. Usually beyond 16K, it's not going to help. And so the question is, how long do you have to wait to get 16K worth of data? Usually not very long if data's coming in pretty quickly. And so actually, our producer is relatively, our client is actually relatively sophisticated about this. So if you turn off if you maximize your, if you minimize latency, it will actually still attempt to batch together any messages that come in at the same time. This is kind of like a group commit in a database. So any messages that happen to arrive at the same time, it will package them together and send them. If you allow it a little bit of extra batching, it will try and wait an extra millisecond. This is kind of like Nagel's algorithm in TCP to just try and batch together a little bit more data and send it out. And that will give you even better throughput. At the cost of whatever you set. Usually a few milliseconds is good enough that will incur extra latency. Okay, so stream processing. One of the things that people miss, stream processing is kind of this weird thing. Most people have probably hear a little bit about it. For a lot of people, it seems like kind of a niche thing. I'm going to try and argue that it's not a niche thing. It just seems like a niche thing. And the reason it seems like a niche thing is because our data actually arrives in a big batch. And so if your data arrives in a big batch, you can only process it in a big batch. So This is actually from the US Census. If you ever talk to somebody who's a software engineer about the US Census, they're always kind of like, I don't know why we do this. Like every 10 years, these people go out door to door with clipboards and they write down everybody who lives in every house. So it's like the big batch data collection. They ship all these clipboards back and they count them all. And then at the end, we basically know how many people we had, except of course by the time you finish the count, the number's wrong, right? And so anybody who is a software engineer kind of feels like, hey, we should just journal births and deaths. And then we would know at every moment in time, but not only at every moment in time, also for every moment in history, how many people there were. And that would be both cheaper to compute, but also a lot lower latency. We wouldn't have to just do it every 10 years. But if you think about the technology that they used when they started doing this, they were literally riding around on horseback and delivering the binders. And so maybe the stream processing approach was not a workable mechanism. But anyhow, the reason this matters is, of course, if you are collecting data in batch, it is very hard to process it as a stream. So if you get a big dump of data into a data warehouse at night, you're not going to process that data as a stream. It doesn't even make sense. You just have a big batch of data. You're going to process the big batch of data. However, I think our finding working with other companies who have done this stuff is once you have everything in your company kind of happening as a real-time stream, you are absolutely going to have a large set of things that process that data as a stream. In other words, process events continuously as they occur. That is kind of the pitch for stream processing. The other pitch for it is if you think about what a company is and what happens in a company, a large percentage of what a company does is kind of by nature asynchronous. And so it does actually kind of naturally fit in that model. I think the reason people tend to think of it as being more limited is actually because a lot of the stream processing infrastructure is kind of limited. And so it's really hard to do anything in the stream processing model. But in reality, I don't think that's a fundamental limitation. I think as this infrastructure gets more developed, I think we'll come to realize that it's actually a generalization of batch processing. And most of the same things you expect to be able to do in a batch-oriented system, you can do continuously as updates arrive. Cool. So what does stream processing have to do with Kafka? Well, basically one of the use cases we had in mind for Kafka was to act as a kind of substrate for stream processing. If you think of stream processing, the simplest thing you can do with stream processing is basically consume out of a Kafka topic, process, and publish it to a different Kafka topic. And somebody else, or maybe you, can consume out of that topic and publish it into a different topic. And you can kind of think of this as actually just sort of a modernized Unix pipes here. If you've ever used Unix, you can kind of cat some input and pipe it into something else and pipe it into something else. And that is not very different from this style of processing. In this case, the pipe is basically a Kafka topic, and the program is some code you write. And of course, the goal is always at the end of this, you've computed something useful, you want to get that into some kind of live data store for serving or some kind of offline system for analysis or whatever. And so that's kind of like a la carte stream processing. But you can actually do it with processing frameworks as well that work with Kafka. So in this model, Kafka is maybe something sort of like HDFS is in Hadoop, and the stream processing layer is maybe something like MapReduce is. And so these stream processing frameworks very often get paired with Kafka. Kafka is kind of the stream, and these frameworks are kind of the processing. And together, I guess it's stream processing. And they're all pretty good. They're all pretty new. So it's like any alpha software, but they're pretty powerful, and they're getting better. So a lot of people who adopt Kafka are doing it in tandem with one of these systems. And one of the reasons that Kafka is actually better for this type of thing is actually that same kind of model for maintaining data as a log that I described. So one of the things these kind of distributed stream processing systems need to be able to do is have one of their processors, which is processing, kind of fail over and restart in the same position it was in the log, not, can't consider those messages consumed. And so the semantics that we have are actually pretty well aligned with that. And you can kind of think of this whole stream processing as basically a modern Unix pipes where you're piping data between systems, which I kind of mentioned. But if you were to kind of take that analogy, one thing you would notice about Unix pipes is it actually doesn't just depend on this pipe symbol. It actually depends on something else, which is data format. One of the interesting things about these Unix command line tools is everyone will point to them as one of the few successful areas of data integration. It's one of the few times we've actually managed to have different people work on different programs and plug them all together somewhat seamlessly. This is actually more or less what we are trying to do, except we're trying to do it at the data center level, where we want to plug all the pieces of systems in the data center together. But one of the other things, in addition to a kind of shared piece of infrastructure, which is that symbol, that the Unix commands all assume is a shared data format, which is plain text. Maybe not the world's most sophisticated shared data format, but you can imagine it would be a lot more painful to use the Unix tools if each command line program assumed a different binary data format, and you had to convert between each of them. And so this was actually another kind of critical element of this stream data platform idea that we had, was to have some kind of shared data format that covered all these different streams so that they all kind of look the same and they all represent fields the same way and you can reason about them. And what this comes down to is schemas. So a lot of people these days are maybe kind of down on schemas, but I'm really pro schemas. I just think they need a few tweaks to be made applicable to an organization where they're going to change all the time. So I think one of the problems in databases was it was a little too expensive maybe to change your schemas, and there was an assumption that you would only have one schema at a given time. Whereas in this world where you're going to have many applications publishing a particular type of data, you can't expect them to all just instantaneously update to the new schema. Of course, many databases actually handled this problem, but a lot of the ones that people use most commonly didn't. And so people have sort of a negative view of schemas. But one of the things we put into practice was actually pairing schemas with these Kafka topics. So internally, Kafka is totally schema agnostic. It just basically delivers byte arrays. It's low-level infrastructure. But our usage at LinkedIn, and what I encourage people to do, and actually what most of these other large tech companies have done, is actually have some kind of standard data format that they represent data. We did it at LinkedIn with something called Avro, which is pretty good. It has a JSON representation and a JSON data model, but it gives you a very compact binary format, and it gives you a language to describe the fields in your data. And this can actually be a really critical tool for managing the evolution of data as it flows. So you can imagine some of the problems I talked about in those first slides of how data was always evolving and everything was breaking because the upstream schemas were changing. This is how I think you can start to solve that problem by actually letting schema changes kind of flow throughout systems and being able to put restrictions on what type of schema changes are legal and what types are not legal. Like being able to give some backwards compatibility guarantees to people who consume data. And this is a topic which is somewhat nuanced and deep, but something I care a lot about, which is basically if you want to make your if you want to get rid of that kind of data munging team, one of the first things you have to be able to do is handle the fact that data is going to get updated in other parts of the organization and reason about what types of changes are OK and what can flow directly in and which are going to be break compatibility and require processing. OK, so anyhow, we put all this together. And we got an architecture that looks something like this. We had Kafka acting as this big kind of bus in the middle. We had a bunch of different things that all kind of published to that or fed off of it. We had stream processing that was happening in applications or also in a stream processing system. This would flow data into the Hadoop clusters. This was the source for log search, monitoring systems, security systems, various real-time analytics systems. Anything which was kind of happening in the company would be kind of captured as a stream. We could process those streams and publish back new derived streams, which could in turn be indexed for serving to live users. So it was pretty cool.
So not just a pipe, but it could also be a DAG.
Yeah, that's right. That's right. I mean, it's kind of obvious, but obviously, if you have one of these topics, you can string lots of them together. So so usage at LinkedIn. Every time I give this talk, this slide gets out of date because it goes up. But yeah, basically, virtually everything that happens in the company is available as one of these real-time streams. There are over 800 billion messages written per day. Almost 900 billion, actually, I was told yesterday. There are about 2.9 trillion messages read every day. There's about a petabyte of data, which is that kind of set of stuff in Kafka. This is connected to by effectively every process in the data center to write operational statistics or what's happening to it. And it's actually used by just a large number of engineers for a variety of different systems. It's also kind of the backbone data flow for a number of different derived data stores that LinkedIn built, including the search system, social graph system, the news feed that you would see on your home page. That kind of all flows in through these topics and goes through this processing layer. And they're actually working on doing the same thing for their kind of primary data store, which is this distributed key value store. So they're actually making Kafka into the kind of primary commit log for that, which is a very cool and ambitious project. As well as the basis for all this kind of stream processing and transformation. And best of all, I got to get rid of my data munging team. This kind of process of the first level of loads into Hadoop went from being this kind of very labor-intensive thing to something that was really just mostly an automated thing. Obviously, that didn't cover kind of higher value transformations we might do on the data later. But that basic problem of, hey, take anything happening in the company and map it into a Hive table, maintaining all the structure, put it in an efficient binary format, that was basically just purely automatic. The metadata flew off the metadata that came with the streams. The data flew in continuously. And then people could publish out new data sets to go out to the live systems. Yeah?
So how do you manage or publish what's installed to?
Yeah, that's a good question. So I'll actually say a few words about that in a couple slides. Yeah. Sorry, I keep forgetting. The question was, can you repeat the question? The answer was yes. I can't repeat the questions. Maybe. The question before that was, can you talk about the topic schemas? And the answer is, yeah, give me a sec. OK, so this is actually now used in a bunch of different places, including eBay, I was told. I don't know if that's true. I just hear these things. I don't know if they're true. And then I put them up on the slide. So yeah, a lot of companies are using this now, which is awesome. We worked on this for years now, and we kind of became increasingly convinced that this is really kind of a future way of managing data flow. If you could have some kind of like central bus of everything happening in the company, that would be really cool. And it makes sense. Like the diversity of different systems is kind of increasing, so this plumbing problem is worse. Data is getting bigger, especially if you're dealing with like event data. I think there's increasingly pressure to deal with things a little bit faster. And we had this piece of technology. And so I guess if you have some kind of belief like this, there's only one thing you can do, which is we quit our jobs. We left LinkedIn and we started a company to try and help make it happen. The company is called Confluent. We're basically taking all the stuff in addition to Kafka that we built at LinkedIn, but actually it's pretty much the same stuff that a lot of these big tech companies that have been working on the same thing, usually using Kafka, have built internally there. So we're basically just trying to productize all that and make it available to people. And you can think of it as kind of like any of these open source companies like Cloudera or Elasticsearch or whatever. We're doing kind of a similar thing for this kind of real-time streams area. OK, so what we have done is actually put together a first version of the product that covers a lot of the schema stuff that you asked about. The way that we're handling this is we basically have some kind of like REST service that maintains the full history of every schema. As your data evolves, you can like update that schema, and it can basically tell you, hey, for this topic, we only allow compatible evolution of schemas, meaning you can add fields, but you can't like change the type of an existing field. Or you can say for this other topic, it's experimental. I don't care. Do whatever you want. And so if you're interested in that, you can go to confluent.io, and there's a bunch of write-ups where we give a bunch of recommendations about how to actually put this stuff in practice, as well as this software. This first version of the software is all open source, so you can download it. You don't need to pay us or even talk to us if you don't want to, although you can. And we've given a bunch of recommendations about practically how to put this into use. Oh, this says first release next week, but that actually already happened. That's out of date. And that's what I got. So if you're interested in this stuff, a couple things. I did a relatively long blog post on how to put it into practice. There's a company website. There's some stuff on Twitter. Kafka itself is, open source Apache project. You can check out the website. You can check out the Twitter for that. I did a relatively long blog post and book on kind of the use of this log type stuff. We're also, since everybody had hiring updates, we are also hiring. So if you're, really like this stuff, then you can come work on it full time. And that's it. I'm happy to answer any questions. All right.
So what is the throughput of this one, like in the per node cloud basis?
Yeah. Yeah, that's right. So the question is, what's the throughput of this system on a per node basis? And so, it'll just let's take replication out of the equation, right? Because every time you replicate, of course, that's like, adding it up. But yeah, you can actually get, it depends on your kind of network speed and your linear write throughput of your disks. But like for a couple pretty cheap hard drives on a machine, reasonable network, you should be able to get on the order of 150 to 200 megabytes per second per machine. And so you kind of add that up over a bunch of machines. It's pretty sizable write throughput. That is write throughput. Reads are a little bit different. Reads are going to be doing linear reads, but generally your readers are actually caught up. So they'll just be reading out of cache, and so there's no real I/O associated with that. But there is network bandwidth associated with it. Does that answer your question? Cool. Awesome. Question in the back.
So messaging systems with transactional ACID properties to the message have been thought about for a while. But there was nothing else out there that came close?
Yeah. I mean, I guess I would argue this is a little bit different in some of the ways I pointed out, right? Basically, like long-term persistence, like keep a petabyte of message data, overall throughput, kind of management as a cluster. I agree. I mean, I think, to some extent, nothing in computer science is new. But yeah, it wasn't like we didn't try. Like we actually started a project with the intention of taking open source messaging systems and turning them into this thing. And that project basically failed. And then we started a second project to build one. So I mean, people at various times have said, well, maybe there's, I think we did actually probably hit the main open source messaging systems people have recommended to me. Maybe some of the proprietary ones are better, but there, I think it's just a cost question. If you're going to have a bunch of these, like it may get pretty expensive. Question?
Why is it called Kafka?
Oh, that's a good question. The question is, why is it called Kafka? OK, so Kafka is a writer. There's Franz Kafka. So the idea was, and this is not that well thought out. I mean, the first idea was it's really important to have ridiculous internal code names for projects. The second idea was, well, it's a system that does a bunch of writes, so we could have, and it keeps a journal, so it could be some kind of writer. And they thought, like, well, this whole area of like connecting systems is kind of like Kafka-esque, right? Like it's like kind of horrible and scary. So, that I think that was the extent of it. It doesn't totally make sense. I wish it was an acronym for something. Question?
Can you talk a little bit about your metadata and schema management you mentioned? Like, are these point-in-time schemas? Are you versioning them?
Yeah. It's like a deep. It's almost like a talk in and of itself, but yeah. So we're using Avro. The schemas represent the events. The service stores actually. The service is kind of like the catalog of a database or something, but it actually maintains the full history of every schema. And to evolve a schema, you basically just push something that uses that new schema, and it will just evolve. What you're allowed to do then is put restrictions on that evolution. And so you can say, look, this is the most important thing. This data stream is the most important one. I only want backwards and forwards compatible changes. Or you can say, like, I don't care. It's experimental. Do what you want. The reason that you care about that is if you're taking that data and trying to just directly project it into Hadoop, it's very common that people will make changes that require you to reprocess your old data in Hadoop. Let's say you have 2 years of history in Hadoop. Somebody makes a change. Now suddenly you have to make the old data look like the new data. It turns out they never thought about how that would work, and there's no way to do it. And then what do you do? And so you need that kind of restriction just to be, to give people freedom, you have to have some restrictions on that freedom. Otherwise, chaos reigns. And so the way we did this was then we were basically, for most of these topics, there was a few that were locked down at LinkedIn, but we would let we would let people evolve their own data formats, and we would just code review the naming and stuff so that it was nice.
So on the same topic, so
Yeah.
these are constraints on the producers rather than also on the consumers.
Yeah, so it's more like a guarantee to the consumer. So I guess if you asked producers what kind of restrictions do you want to have on data, they would say none. If you asked consumers how restrained should producers be, they would be completely constrained. Let's like write down the schema and it will never change. And so it's really some balancing act between those two. So what you're trying to guarantee consumers, there's actually two guarantees you're trying to give. One is I want it to be the case that new data can look like the old data. Why do you want that? Because like, let's say you build an application which consumes one of these streams. It was built at a point in time. When your data evolves, it doesn't evolve at exactly the same time. And so if you don't have that property, you're not compatible with that application. The other notion, I would call that forwards compatibility because you want your application to be compatible with the future. The other notion of compatibility is, hey, I have 2 years of history in my Hadoop cluster. When I publish new data and put it in Hadoop, I want to evolve my Hive schema, but I need to be able to read that old stuff as the new stuff. That's backwards compatibility.
Put the question the other way around. So I'm a producer and I have a bunch of consumers.
Yep.
I want to migrate to a new
Yep.
data model.
Yep.
How do I know that all of my consumers are aware of the new data model and can consume the new data model and I can switch over?
OK. Yeah, so the question is, if you're evolving, as a producer, if you're evolving a data format, what do you have to do for consumers? And the answer is nothing, as long as your evolution meets their compatibility requirements. In other words, as long as your new data can look like the old data. So if you go through common cases, let's say you add a field, that's going to be fine for them. They will not see that field because they were written in the past when that field didn't exist. If you try to change a field that they are using, which is an integer, and you try and make it a string, that is going to break them, and that is an incompatible change. And so what you want to be able to do is give some kind of calculus for the producer who's making this change to reason about whether their change is compatible or not. Now, of course, there's deep levels of incompatibility, like, well, there used to be a string, and there's still a string, but now the meaning has slightly changed. You can't catch everything. But these kind of syntactic changes are like the big bulk of problems, and this basically helps make that more mechanical, if that makes sense.
Do you have a, sorry, but just a follow-up, do you have some sort of broker system that's making sure that the serialization and deserialization on both ends match up? And where are these schemas stored? Like, it can't be in the cluster itself.
Yeah, actually, OK, so people love the schemas. This is good. Yeah, so there was a bunch of questions there. One was where the schema is stored. The schemas are basically made available by this REST service. The backing store is actually a Kafka topic, I guess, because we figured you got to have that if you're running this thing. I think what was the next question? How do you make sure producers and consumers agree? Right now, we don't enforce that. We may add some enforcement at the broker layer. But yeah, right now, it's a by convention.
I mean, but if it's like a JSON record going through, you've got all the field names coming in and out.
Yeah, so I mean, the assumption is you are adopting this. And my recommendation would be, do this at a company-wide level. Just have some data format that everybody uses. There's usually no reason to do it topic by topic, in which case they're all the same. Everybody just uses the same serializer plugin. Questions?
When setting up the nodes, is there a rule of thumb on how to best determine like the RAM requirements?
OK, so the question is how much memory do you need? So Kafka itself, the process, doesn't use much memory. It immediately writes stuff to disk, to the file system, I should say. And the process itself, usually a couple gigabytes is fine, which I guess these days isn't a lot, although it seems like a lot. So what memory gets used for is primarily for the operating system cache. The operating system cache will allow it to buffer writes and delay them a little bit, so it can do these nice linear writes. Normally, people are very scared of that. It's usually OK. You can force an fsync on every write if you want to. It's usually OK in our model because we have replication. So unless all your nodes all fail at once, you're usually OK with that. And so that is what RAM is used for. It's used for buffering writes and caching reads. So obviously, that same write will now be cached for the reader. And very commonly, the pattern in a messaging system is you write a message, and a bunch of readers read it. So that works really well. Question over here.
Can you compare with AWS Kinesis?
Yeah. So the question is, how is this similar or different to Amazon Kinesis? It's extremely similar. I think that system was in part inspired by this one. APIs are pretty similar. Consumer models pretty similar. This is basically an open source thing, and that's a hosted service. But I would say if there's a bunch of nuances, but at a high level, it's basically the same difference. The one as a service, one open source. There's a bunch of nuances, like we do these key compaction for mutable data, and we have a bunch of different features, but it's really that's in the details. High level answer is, yeah, they're pretty similar. Question?
So back to the schema topic. So my understanding of Avro is that the schema is built into the data itself.
Mm-hmm.
So that's basically what you get for free in terms of you don't have to have any additional infrastructure to have the client or producer.
Yeah, that's not quite right, actually. So the data in Avro is actually just the bytes. There's no schema information, which is basically a separate piece of information, both of which you need. Yeah, so JSON, everything's built in. Thrift, maybe some tags are kind of half there, and half of it's in your code. Avro, basically, almost nothing is built in.
Okay, so you're saying the schema is not part of the payload?
The schema is not part of the payload, which is actually kind of a good thing. If you think about what the data in one of these Kafka topics, it's like the same fields in every message. And so if you use JSON, you basically repeat that field information every single time. And so it ends up being the case that half your data is basically field names. And then everybody starts making these really small field names that are like one letter, which, I mean, it's terrible, right? So the question is, Kafka uses Zookeeper. Is the future version of Kafka going to not require Zookeeper, which is usually followed up by the future version of Kafka should not require Zookeeper?
What's the state of that? How soon are we going to expect Kafka to be?
Yeah, don't hold your breath. So yeah, Kafka does depend on Zookeeper, which is a system which helps do some of the coordination. We are doing a bunch of projects to remove any Zookeeper interaction from the clients. Why are we doing that? There's so many clients in some of these deployments. It's just very hard to manage Zookeeper if you have everything connecting to it. It would be nice. That project is going on as part of work on the producers and consumers, and is kind of a big ongoing thing. Should be finished by the next release. We've done a bunch of prior things to get the storage of consumer positions out of Zookeeper and other stuff out of Zookeeper. But then, when that happens, Zookeeper will be basically like an implementation detail of the Kafka cluster. You still might want to get rid of it, just, I don't know, for overall simplicity. We're not working on that right now. It might be nice, but Zookeeper does work pretty well, and so replacing it means you need something else internally that does that kind of coordination that would work equally well. Okay, there's a bunch of ways to think about reliability. One way is kind of like, what are the guarantees that the system provides? The guarantees in this case are relatively strong. The other is kind of like, is it actually being used, and do you have any kind of external check on correctness? Yeah, so one of the systems that we had at LinkedIn, we called it Audit, but it actually validated what the producer thought they sent against what the consumer got. And we did that actually continuously in real time. It's only inside LinkedIn. Well, if only, well, it's the same software. Well, the validation is only in LinkedIn. Well, let's follow up. I mean, yeah, it's heavily used. If you want to get more information on how reliable, I mean, I would say it's heavily used. If you have something which requires large scale, I would say this is much better than whatever you're going to build yourself. If you have something which doesn't require large scale, I don't know. Maybe you can use like Oracle, and that's been around longer. But yeah, it's built to be reliable. It's not known to lose data. So what I'm saying is this. We ran this for 5 years. We had something which it did an exact audit of what came in and what came out. And we had to pass that audit. And that's actually pretty hard to do. That software is the same software that's open source that everybody's using. We haven't made available that audit tool, but the company that I'm part of is only a few months old, so give us some time.
Back to schema.
Yes.
In my user case, we have data coming from old schema and new schema all together in the base.
Yes.
Would we know data come from which schema when we put the map?
Yeah. So the question is around schemas, and the use cases, there's both the old schema and the new schema kind of both coming together. Would you know? Yeah, this is really important. So one of the things we've tried to model is the fact that schemas don't just change instantaneously. Like whatever somebody's view of the data is changes only as that application changes. And so yeah, each message in this system, the schema stuff is, by the way, an add-on to Kafka. You can use Kafka with any kind of bytes. You don't have to use the schema system. We think it's a good practice. But if you do use it, yeah, each message is basically tagged with the exact schema. It's tagged with an ID, which matches to the exact schema that was used to write it. And so you know exactly what it was used for. And based on those kind of guarantees, you can project it forward to a different view, either the current latest schema or some past version of the schema that you had when you wrote your application. So yeah, that's one of the things we're trying to make possible. Question?
So I was thinking about the SLA that you mentioned earlier, and it seems that it may be a little over-constraining. So if you have the space, you can write more logs. And I was wondering if you've been thinking about sort of dynamically, keeping track of more data based on what consumers have or have not yet consumed.
Yeah. Okay. So I think the question is.
So basically, keep more data around if there's a consumer that hasn't, it's a little bit early on in the time.
Yeah, so the question is, could you kind of optimize what data is retained based on where consumers are? And if you don't do that, doesn't that waste disk space? And the answer is, it does waste disk space. But if you think about it, well, maybe in a system like this, disk space is actually super cheap. The constraining factor is actually disk throughput, so basically write throughput. And so basically, like keeping the bytes on disk is not a big deal. In fact, like for especially these like cheap SATA hard drives, I mean, like getting bytes is like the least of your worries, right? In all the things you're paying for. So, so I would try and claim it. It's actually not a huge problem just to like maintain that history. Potentially, you could try and be smart about when you truncated different logs based on when consumers are, but that doesn't really attack your critical bottleneck, and it actually also limits the consumer API, because one of the critical things that we do that makes this work well for like stream processing systems is you can actually fail over and move back in time to your last saved spot. And so if I had said, oh, that consumer was already past that spot and truncated it, of course I couldn't do that. So I do think that ability to kind of move backwards in time for a variety of reasons, either because you're restarting your ETL load or you're running some load process is actually pretty important.
So essentially the motivation here is oftentimes sort of new consumers are sort of experimental and they're not optimized for speed.
Yeah.
So you have these consumers that have these great ideas, but the implementation is relatively immature. And eventually they get to better speed, but the initial consumption is
yeah, so you're basically flagging a case where a consumer is particularly slow. And I would say actually in that case where the consumer is slow, having this defined retention is basically awesome. Because what happens is, imagine a messaging system which just retains messages that haven't been read by consumers. And let's say that you want to have very kind of easy access. So any experimental thing can plug into one of these data streams. Well, everything's running fine. You're basically not maintaining a lot of messages in your queue because everybody's caught up. And then maybe this person uses this kind of command line console tool to plug in, and they, of course, can't keep up. And so then what happens, all of a sudden your retained data explodes and the whole performance of the system changes. So it's not really very good, right, if you want to be able to make data available to readers, and the readers can't be forced to keep up if your retention is all based on what's been read and what hasn't. One of the reasons this is nice is there's basically no real performance, significant performance hit for these slower reader cases. You got the data there anyway. They're just at a different point in the log. So I guess that's the motivation. Yeah, question?
At Confluent, you have support for REST APIs instead of native libraries. Is that a temporary solution, or what is the?
Yeah. So one of the things we just did at Confluent was release a set of REST APIs. We did that because people wanted it. Why do we have a REST API and a kind of native API? The native API is basically a direct connection to the partitions that have your data. It's super high throughput. It's good for managing partitions. It's good for kind of like more controlled access to data. If you were going to build like a stream processing layer, you definitely want to use the like native access. If you're building something decoupled, you don't. So one of the things we're trying to do is make APIs work in all the different languages that people use. And it turns out that there's basically a set of languages, maybe the top 5, which cover a lot. And we're going to try and get really high quality native clients in each of those languages so people can do rich stream processing just directly in that language. But then there's like a long set of things like COBOL. Like, are people trying to use COBOL with Kafka? Yes, they are, it turns out. Are we going to have a native COBOL client? No, we're not. So REST seemed like a good answer there. Question?
So a couple of things. One is how is the adoption? I mean, contributions to the open source project. Is it a very active project? Is it a very active project?
Yeah. So the question is, is it a very active open source project? Yeah. The answer is it's actually quite active. If you can go check out like the mailing list archives or whatever. There's thousands of emails a month. There's pretty significant now code contributions from a bunch of different companies that either run this internally or are otherwise working on it. Confluent has a bunch of people working on it. LinkedIn still has people working on it. So now, actually, yeah, there's a bunch of development happening. We have almost the other problem, which is there's a bunch of people trying to all do work on the same code base, and you have to get it all to the right level of quality.
And a follow-up kind of question. So for enterprises looking to adopt Kafka, what would be the first step in terms of, as you mentioned, we have data all over the place, legacy systems. So how do we get started with that?
Well, you should definitely come talk to us. Besides that, oh well.
No, I can give an example of, like, let's say this data in the database or databases. So would you recommend that we actually, how do you instrument so that?
Yeah, that's right. You're saying how do you connect this up to all these systems? That's actually a problem we're trying to attack directly. So like right now, if you go to GitHub, there's like 500 Kafka integrations, but it's very hard to like run them all. They're all like open source. They're in different levels of quality, whatever. So we're trying to make a framework that makes running these kind of integrations or connectors common across. And hopefully that gives away, we still want them all to be open source, but hopefully that gives away that if you're running multiple of these, they kind of all plug in easily, and we can take at least top systems and kind of get those things in shape. We haven't done that yet because we're a very new company, but soon. So right now I would say like there's basically this producer and consumer API. There's pretty good integration with Hadoop. There's some good integrations here and there, but yeah, you're probably going to be writing some code in the very short term.
How about with Spark?
The integration with Spark has historically been pretty bad, but they're working on it, and the newest version they just released is actually significantly better. So they released
the Spark group?
Yeah, Databricks, the Spark project, I guess. So they traditionally there was just a lot of data loss problems for anything that fed their streaming module, and for a bunch of reasons, and they've kind of rewritten that part so it doesn't lose data all the time, which is awesome. So yeah, I would probably try the new experimental thing, which sounds scary, but the old non-experimental thing was basically had a lot of issues. So that's what I would recommend. Question?
Yeah, I was going to ask you about Spark. Basically, if our installation has only HDFS and we don't have any dependence on Hadoop and all, and we want to install Spark and use that, then can we assume that the Spark streaming functionality, the latest one, 1.2, will supplant this, and there's no need for Kafka?
Yeah, I mean, it depends. I guess Kafka is kind of like HDFS for real-time streams. So if the data you want is basically in HDFS, I think you can run streaming against that, and there's nothing wrong with it.
Or even to get into HDFS, you could use Spark streaming, right?
Yeah, potentially you could use the connectors. Yeah, I think Kafka is more equivalent to HDFS than it is to Spark itself, if that makes sense. Yeah.
Is Confluent going to do something with Samza, or is that above your?
Yeah, right now we're mostly focused on this lowest level of just like making the data available, making these streams available between systems. So we're not doing any like stream processing stuff quite yet. Other questions?
So going back to schemas, you mentioned that the average schema is also held as a topic inside of some Kafka cluster, correct?
Yeah, I mean that's basically an implementation detail of how we're storing them in that service.
I was just curious. It sounds like in my understanding, anything that is held inside of a Kafka cluster has a very small time window, right? Could be 7 weeks or whatever. So what sort of durability guarantees do you guys provide for schema, which needs to probably live for much, much longer?
Yeah. So the question is, okay, you said you were holding schemas in a Kafka topic. How can that be, given that you only hold stuff for 7 days, basically? Yeah. So yeah, actually, you can hold stuff for as long as you want. I mean, it's basically a replicated store. And so obviously in that topic, we hold it. We actually hold it forever. We have the complete log of schemas there.